Okay, welcome to the 11.2 notes video where we're looking at the next introduction to calculus concept. So in the last section, we were looking at the derivative, which we said is also described as the slope of a tangent line. And we also said it can be described as the instantaneous rate of change. And graphically, what that looks like is if I have some function, if I want the derivative of a point, I would just say, here's the point. I need to find the slope of the tangent line, and there's a formula for that. I can do it for any point on a function, or I can do it for the whole function, in which case I'm looking at f prime of x, which is going to give me a function back. Okay, we're going to use kind of the opposite of that concept now to find the antiderivative. Okay, so this section is kind of about the antiderivative. And in order to find the antiderivative, which we also call it the integral, it will need the limits as x approaches infinity. So think back to in our previous chapters when we were using limits, right? When we said the limit as x approaches infinity, we're talking about the end behavior of the graph. And if there was a horizontal asymptote, so if the graph leveled off, we said that the limit was some value and we called it L. So we're going to keep using that notation. This limit as x approaches infinity has a limit, then we'll call it L. Okay, the first example that we're going to take a look at, we're not going to need limits for this example. We're just going to look at kind of how is this the opposite of what we were doing in the last section. So in the last section, we started out with a velocity problem, familiar to us that we've been doing speed problems for a while, distance, rate, and time, right? So we're going to kind of start out with that same idea. But this time, instead of solving for velocity, we're going to solve for distance. So we need to manipulate the equation a little bit. So we have an automobile that's traveling at a constant rate. That's important, right? It's traveling at the same speed, 48 miles per hour, for 2 hours and 30 minutes. Now, I know I'm going to be multiplying, so I want this to be in constant units. So I'm going to change this to 2.5 hours. How far does the automobile travel? So we want a distance. So what is the distance if I have a velocity of 48 miles per hour and a time of 2.5 hours? So I'm going to set this up similar to how a lot of chemistry problems are done. We're going to put the units so that we can see that they cancel out. So we have 48 miles per hour times 2.5 hours. And so I can see that the hours will cancel out. And 48 times 2.5 should give me 120 miles. Okay, so now the question is, how does that change if instead of traveling at a constant rate, we're traveling at an average rate? And the answer is the calculation itself doesn't change. What changes is the meaning. Okay, so we're going to look kind of at a graphic representation of these in a few minutes, but first I want to just look at algebraically, how does the computation look? So again, we have a rate, or our velocity, and we have a time. I'm going to change it to 2.5 hours so that it's 1 unit of measurement. How far does the automobile travel? So the same calculation, 48 miles per hour, and the same time, 2.5 hours. Hours cancel out, so we're left with 120 miles. Okay, so we get the same answer to both questions, but it's the meaning of the questions that's different, right? At any point in time on that 2.5 hour journey, I was traveling 48 miles per hour in example 1. Whereas in example 2, at any point in time on that 2.5 hour journey, I was probably not traveling 48 miles per hour. 48 miles per hour is just my average, right? So I could have been driving 30 miles an hour on part of the trip and 65 miles an hour on another part of the trip, but the average speed for my whole trip for that 2.5 hours was 48 miles per hour. So it's the meaning of the question that's different, not the answer to the question that's different. Okay, so if we wanted to find an instantaneous distance, the distance at any point along the journey, for a constant rate, that's easy, right? I would just change my time to the time that I want on the journey. Whereas for an average rate, it gets more complicated. And the way we can find that, if we're given the function of the rate of change, so if we're given the speed, then what we do is we find the area under the curve. Okay, and I'm going to show you a graphic representation of example 1 and 2 and how that looks different, areas under the curve, at the beginning of the next page. But first I want to talk about, okay, so when I'm calculating that area under the curve, like we mentioned in the vocabulary section, we're going to need limits. So let's review, how do we find limits? Okay, so there's this kind of scenario here. We're looking at teacups, and water is being poured into the teacups. So we start with 10 teacups. We have a gallon of water, and we want to know how much water is in each teacup, how much water is in each of the 10 teacups. So if I have 10 teacups and I have a gallon of water, each cup has 1/10 of a gallon. And then how much water do I have total? Well, if I have 1/10 of a gallon and I've got 10 teacups, that's 1/10 of a gallon times 10 teacups should give us 1 gallon, which we expected because we had 1 gallon to split between each of the teacups. So what happens if we have 100 teacups? Well, then I have 1/100th of a gallon in each teacup if I'm splitting them evenly, which means that the total amount of water I have is 100 teacups with 1/100th of a gallon in each one. So again, I should get 1 gallon. Okay, so then what if I have 1 billion teacups? Well, now I have 1/1000th of a gallon, 1,000, million, billion, in each teacup, which means how much water do I have altogether? Well, I have 1,000, million, billion, 1/1000th of a gallon in each teacup times 1 billion teacups gives me 1 gallon. Okay, now if I had 1/1000th of a gallon in my teacup, that'd be like a drop. It's very small, right? So then when we get up to an infinite number of teacups, how much water do I have in my teacup? Well, if you think back to when we were doing limits before, as I keep splitting it up over a larger amount, the amount that I have in each is tiny, right? But in order to mathematically show this, we have to use limits. So example 3 is kind of how do we answer question 4? Okay, so we want to write an equation for the amount of water in each teacup and an equation for the total amount of water. So let's start with the amount of water in each teacup. In each teacup, we have 1/n amount of water, where n is the number of teacups, right? And we want to know what happens when n goes to infinity. So we say the limit as n approaches infinity of 1/n. Now this is familiar. We've seen this before. We've done this with functions, and we know that as n approaches infinity, 1/n approaches 0. So the limit is 0. Okay. Now if I said I have 0 water in each of my teacups, and I have an infinite number of teacups, we might be tempted to say, well, then 0 times infinity equals 1 gallon. But we can't multiply 0 by infinity, right? Because infinity is not a number. And we know that 0 times any number should be 0. So then how is it that 0 water in each teacup times an infinite number of teacups adds up to a gallon? Well, again, we need limits. So we're going to go to find the total amount of water in each teacup. My equation was 1/n times n, 1/n times n, right? So we're going to have the limit as n approaches infinity of 1/n times n, which is the limit as n approaches infinity of n/n, which is the limit as n approaches infinity of 1. Well, no matter what n is, our limit here is 1. Okay, so that's how we can see, using limits, this idea of splitting something into teeny, teeny, tiny pieces. If I can keep splitting them until there are an infinite number of pieces, just meaning that if I can split it, I keep splitting it, and I can always keep splitting it. Okay, then what we end up with are these infinitesimally small pieces. So we have essentially 0 water in each teacup, and yet the total still adds up to a gallon because that's how much water we had split. Okay, so this is how, this is how we can use limits in order to find these values having to do with infinity. Okay, so let's look back, and you're going to want to keep access to example 1 and 2, because now what we're doing is we want to, got my pages scrambled, look at example 4, where we are graphing example 1. Okay, so to start with, if we're graphing example 1, we need to graph distance and time, right? But we don't have distance as a piece of information, so really what we're graphing is velocity over time. Velocity over time, because those are the two pieces of information that we know. So time, let's say each of these dashes is a half an hour, so that's 1 hour, 2 hours, 2.5 hours. That's how much time we're looking at. Okay, and then the velocity in example 1 was constant, so 48 miles per hour. Now I'm just going to pick a dash because I'm not going to scale this, and I'm going to say that this is 48 miles per hour. Okay, so then how do we find the distance? That's what we were asked for in example 1. So how do we find the distance? Well, we took the 48, right? This distance here is 48, and we took the 2.5, and we multiplied them, meaning we got the area inside here, and that was 120 miles. And so you see how that 120 miles represents an area underneath the curve of a constant 48 miles per hour, right? This would be y equals 48 if we were to find it as an equation. The speed at any given time was 48 miles per hour. Okay, well, what about example 2? How does that change? Well, we had the same window of time. We still had 2.5 hours. Okay, and our average was still 48. But that doesn't mean that our speed at any given time was 48. That means that if I take all of my speeds and I average them together, it was 48. Meaning some of my speeds were below, some might have been above. But if I take all of those speeds and I average them together, I should get 48 miles per hour. So this is an approximate graph of what my speed could have been during that 2.5 hour window. Okay, but the average of 48 is still the height of a rectangle. So this height of the rectangle is still 48 miles per hour. And the width of this rectangle is still 2.5. And so that 120 still represents the area under the curve. However, now our f of x is not a constant rate. So I can't give you a function for f of x. I wasn't given that information, right? But it's still the area underneath f of x. So then the question becomes, well, how do we find the area under a curve if it's not a rectangle? Okay, so in example 5, we're going to look at how do we approximate this area. And what I'd like to do is I'd like to review some of the areas that we know, some of the formulas for area that we know. So think back to geometry. We know that the area of a rectangle is base times height, or length times width if you prefer, right? We know that the area of a triangle is 1/2 of that, 1/2 base times height. And the base and height have to be perpendicular. Okay. We also know that the area of a circle is pi r squared. And so the area of a semicircle would just be 1/2 of that. And then one that we might not be as familiar with is the area of a trapezoid. And we'll see why this is so important. The area of a trapezoid, which is 1/2 base 1 plus base 2 times height. So kind of like a triangle, but with 2 bases, right? So we have 1/2 base 1 plus base 2 over height, and base 1 has to be parallel to base 2. Okay, so those are kind of our areas that we can recall from geometry. Well, in example 5, we're using rectangles, kind of our basic area shape, and we're approximating the area underneath this curve. Now, we don't have the tools to approximate the area yet, but we can, or to find the exact area rather, but we can approximate it by making these little rectangles. that approximate the area. We can get close, okay? So notice these rectangles all touch our function on their right side, okay? So the boxes touch the function on their right. So we call this a right rectangular approximation method. Approximation method. Abbreviated RRAM. Okay? Now, if I made the boxes from the function on the left point, then it would be a left rectangular approximation method. Okay? So really we're saying, where do these boxes touch the graph? If it's on the right of the box, then it's a right rectangular approximation. If they touch on the left, then it's a left rectangular approximation method. Okay? And if we're looking at this, we're going to need to find the area of each of these rectangles. And so we need the base and the height. Well, the base here, 1/2, because these are evenly split, we know that each base is 1/2. But in order to find the height, I need to evaluate the function. So I need to find f of x. So let's find these functions. Well, this is 1/2 comma squared 1/4, right? Because we're plugging it into f of x. This point here is 1/1. This point is 3/2 comma 9/4. It's easier for me to square fractions, but if you prefer decimals, you can do decimals and use your calculator. This is 2/4. This is 2.5, so 5/2, 25/4, and 3/9. Okay, so now that I've evaluated all of those points, I can find the area. Area equals base times height plus base times height, and I'm going to do that for each of these 6. So the base is 1/2 times the height is 1/4, plus, again, my base is 1/2, and my height is 1, plus now my base is 1/2 and my height is 9/4, plus a base times height plus base times height. I'm just looking at the y values here, and the base is the same for each of them. Okay, now notice in order to calculate this, I could put it all into the calculator, but they all have that same base of 1/2. So I can also calculate this by factoring out the base times adding up all the heights. Okay, which is 1/2 times, I'm going to add up all the fractions here. 10 and 25 is 35/4. 5 and 9 is 14. Okay, and from here, I would absolutely use a calculator. Okay, but make sure you're grouping your parentheses properly. So 1/2 times in parentheses 35/4 plus 14. Okay, and what you should end up with is 11.375, or in a fraction, that's 91/8. Okay, so notice, what did we do in order to find this area? Well, we just added up a bunch of rectangles, and they all had the same base, which was how far over did it go in x. So we can call that the change in x. So we're going to call this the change in x, times the height, which was our y value, not our change in y, but the whole y value, right? It's the whole value from the x-axis to our point. So if we get smaller and smaller rectangles and we place each rectangle with a right-handed point, we can get a closer and closer approximation of our area, right? If I cut these in half, all of this extra area will go away. And if I cut this in half, all of this extra area will go away. And so we'll get closer and closer and closer to our exact area. Okay, and so when we're looking at these values, these approximations, we can use the summation notation where we're adding up all of the triangles, or rectangles rather, we're adding up all of the rectangles, with our base as the change of x and our height as f of x for each of those triangles, or rectangles. I'm sorry, I keep saying triangles. So our first rectangle would be x1, our second rectangle would be x2, and so on and so forth. And the smaller we get those rectangles, the smaller we can make our change in x, the more exact our area will be. So we've finally come to a point where we can define our integral. So a definite integral, meaning that it's an integral where we know the interval that we're looking at. We know where we're looking for the area, okay? So if f is a function defined on the interval a to b, so we have our endpoints, and our summation of heights and bases is defined as above, so how we did it in our last example, the definite integral of f over our interval is this notation. Okay, so we say the integral from a to b of f of x dx. So that tells us our distance, our change in x is what we're looking at, our rectangles. Okay, and we say that that's the limit as the number of rectangles goes to infinity. So as our rectangles get smaller and smaller, so we get more and more and more rectangles, our area gets more and more exact. And so once we have an infinite number of rectangles, we'll have our exact area. There will be no space outside of our curve that we could cut out, okay, if the limit exists. And remember, there are some cases where we cannot calculate the limit. That's when the limit would not exist, okay? And that means that the graph is integrable. So the integral is what we calculate. Our ability to calculate it is integrable, okay? We will focus mostly on linear cases. So when we're calculating these integrals, right now I'm just kind of defining it, setting the groundwork for calculus. So we're going to focus mostly on linear cases, okay? Meaning that you just have to know how to calculate the area under a curve. Really, when I'm asking for an integral, I'm asking for the area under a curve. The exception is we can also include any shapes in the side note above. So that means triangles, circles or semicircles, and trapezoids are also fair game. Okay, so let's look at an example that's nonlinear, but also it's not a curve like this, okay? So another shape that we know how to calculate, but it's not just a line. So for example 6, we're looking at the integral from 1 to 5 of 2x dx, okay? So the integral from 1 to 5 of 2x dx. And just kind of a fun fact, this symbol for the integral is lowercase sigma. So remember, sigma was the sum, lowercase sigma is the integral, but these are both sigma. Kind of the capital and the lowercase of sigma. So what does this mean? Well, it means that we need to graph 2x. So 2x plus 0 goes through the origin. This is f of x equals 2x. And we want to graph it from 1 to 5. So I want to go from 1 to 5. And I want to calculate the area under this curve. So f of 1 times 2 is 2. F of 5 times 2 is 10. And now we have all of the information we need in order to calculate this integral. So the integral from 1 to 5 of 2x dx equals the area of a trapezoid. If we need a reminder, the area of a trapezoid is 1/2 base 1 plus base 2 times height. And the bases have to be parallel. So where are my bases? Well, these cannot be my bases because they're not parallel. These have to be my bases. So this base has a distance or a length of 2. This base has a distance or length of 10. And the height, which is perpendicular, has a distance or a length of 5 minus 1, which is 4. So we have 1/2 base 1 plus base 2, and it doesn't matter which one you put as base 1 or base 2 because addition is commutative, times the height. So this is 1/2 times 4 is 2, times 12 is 24. I don't have units, so we'll just leave it as 24. Okay, if you're not comfortable with trapezoids, you could split this into a rectangle and a triangle and calculate it that way as well. And you'll end up with the same value. Okay, so this is just kind of practicing. What does it mean to calculate the integral? To calculate the integral, it means we're finding the area underneath a curve. Okay, our last example here, example 7. Suppose a ball rolls down a ramp so that its velocity after t seconds is always 2t feet per second. How far does it fall during the first 3 seconds? Okay, so again, we have a graph. This time we're graphing 2t. F of t equals 2t. And we're interested in the first 3 seconds. So that's from 0, 1, 2, 3. 0 to 3 seconds, okay? Now we're not asking for the velocity at 3 seconds, which would just be f of 3, right? We're not asking for the velocity. We're asking how far does it go? What is the distance that it travels? And the distance that it travels, again, is the area under the curve. And so to find the area under this curve, we have a triangle with a base of 3 and a height of 3 times 2 is 6. Put it into the function. And so we have a height of 6. So our area, which we can also call the integral from 0 to 3 of 2t d, what's my variable? T, equals 1/2 base times height, which is 9. This time we do have units, and our units for how far, distance, are feet. Okay, so I'd like you to look back over the section, think about these problems, think about the definition of an integral, write a summary, and go ahead and put it into Edpuzzle.